So hi friends, this is your Prashant sir, welcomes you to the world of physics from KH Patel PU College, Hubballi. So today in my sixth lecture, I am going to discuss one of the most important and interesting concept as nuclear physics is concerned. That is nothing but the mass defect of a nucleus. So I told you that this is very important as nuclear physics is concerned. Listen carefully. And as the examination is also concerned, it is very important. So listen carefully. So what is meant by mass defect? What is meant by mass defect? So before going to the concept of mass defect, we have to know how the nuclear mass is determined. So while explaining the properties of nucleus, I explained about nuclear mass. So what is nuclear mass? Nuclear mass is the sum of nucleons present inside the nucleus. Is this clear? So what are the nucleons present inside the nucleus? There are protons, there are neutrons. That means the sum of masses of all protons and all neutrons will give you the nuclear mass. Is it clear? So what is the formula for nuclear mass? It is, we have already discussed that thing. That means Z, where Z is the number of protons present inside the nucleus. That is nothing but the atomic number. This will give you the number of protons present inside the nucleus, and it will be multiplied by mass of protons. Mass of protons. So Z is the number of protons present inside the nucleus, and MP is mass of individual proton. If this multiplication gives you the total mass of protons present inside the nucleus, and plus A minus Z. A minus Z will gives you the mass of the total number of neutrons present inside the nucleus. A minus Z will gives you the total number of neutrons present inside the nucleus, and if it is multiplied by mass of each neutron, then it will gives you the total mass of neutrons present inside the nucleus. ZMP is the total mass of protons present inside the nucleus. A minus Z into Mn, the total mass of neutrons present inside the nucleus. So sum of these two will gives you the nuclear mass. That means ZMP plus A minus Z into Mn will gives you the nuclear mass. So this is one of the procedures to find out the nuclear mass. So in another way, what we will do is, instead of taking the masses of nucleons, we will directly measure the mass of a nucleus. That means instead how many protons are there, will not concentrate how many protons are there, how many neutrons are there, will not multiply proton number with the mass of proton, neutron number with the mass of neutron, but directly we will take the mass of nucleons. Nucleons direct ತಗೊಂಡದ್ರ mass ತಗೊಂಡ್ಬಿಡ್ತೀವಿ. So this is one of the procedures. That means directly we will measure the mass of nucleons. So in both the procedure, we are measuring the mass of a nucleus only. Mass of a nucleus only. So one is actual mass. That means we will directly measure the mass of a nucleus. In another way, what we will do, we are indirectly measuring the mass of a nucleus. That means the masses of protons, masses of neutrons, the sum of masses of proton and neutron will give you the nuclear mass. But what happens here? There will be the difference between these two masses. There will be some difference between these two masses, and that difference is nothing but mass defect. And that difference is nothing but mass defect. So look at the definition here. The difference between the sum of masses of nucleons. So here it is, sum of masses of nucleons forming the nucleus. Sum of masses of nucleons forming the nucleus. That means the mass of a proton plus mass of a neutron will gives you the mass of nucleons forming the nucleus, and actual mass of the nucleus. So actual mass of the nucleus. So sum of masses of the nucleons will given by the formula ZMP plus A minus Z into Mn. Here it is, ZMP plus A minus Z into Mn, and actual mass of a nucleus will be given by capital M, will be represented by capital M. Here it is, capital M. Then the difference between these two is nothing but mass defect, and it is denoted by delta M. And it is given by the formula here. Delta M is equal to ZMP plus A minus Z into Mn minus capital M. ZMP plus A minus Z into Mn is nothing but the sum of masses of nucleons forming the nucleus, and minus capital M. Capital M is nothing but the actual mass of the nucleus. That means we will directly measure the mass of a nucleus instead of taking the masses of their nucleons. will directly measure the mass of nucleus. That is nothing but the actual mass of nucleus. This difference between these two is nothing but mass defect. Difference between these two is nothing but mass defect. So once again, look at the definition. The difference between sum of masses of nucleons forming the nucleus and actual mass of a nucleus is called mass defect of a nucleus. The sum of masses of nucleons forming the nucleus and actual mass of a nucleus. Sum of masses of nucleons forming the nucleus is nothing but ZMP plus A minus Z into Mn, minus the difference. What we have to subtract here? The actual mass of the nucleus. That is the thing, but capital M. It is given here. Delta M is equal to ZMP plus A minus Z into Mn minus capital N. And always the mass defect is represented by delta M. So this is about mass defect. So one more question comes in our mind, that is why there will be the mass defect? Why there will be the mass defect? So that will be explained by one more concept, very important concept as nuclear physics is concerned, and that is nothing but the binding energy of a nucleus. Look at here, what is meant by, first we will try to understand what is meant by binding energy. Binding energy. So we know that the nucleus contains protons and neutrons. That means it contains nucleons, right? So all these nucleons are tightly bound with each other with a certain force. That means with certain energy. With certain energy. So if we have to separate these nucleons, that means to separate these nucleons, we have to apply an external energy. We have to apply an external energy. The amount of energy required to separate the nucleus into its constituent nucleons. The amount of energy required to separate the nucleus into its constituent nucleons is nothing but binding energy. Is nothing but binding energy. The amount of energy required to separate, required to break the nucleus into its constituent nucleons is nothing but binding energy. The definition is given here. Look at here. The binding energy, binding energy of a nucleus is equal to the energy required to break up the nucleus. The energy required to break up the nucleus completely, look at the word completely, into its constituent particles, or it is nothing but constituent nucleons. That means the amount of energy required to separate all the nucleons present inside the nucleus. All the nucleons present inside the nucleus. That means if we apply this much amount of energy, then all the nucleons will separate. All the nucleons will separate from its nucleus. That amount of energy is nothing but binding energy. So how much amount of we have to spend there? So how much, ಎಷ್ಟು ಅಮೌಂಟ್ ನಾವು ಅಲ್ಲಿ ಇನ್ವೆಸ್ಟ್ ಮಾಡ್ಬೇಕ್ರಿ, ಎಷ್ಟು ಅಮೌಂಟ್ ಆಫ್ ಎನರ್ಜಿಲಿ ಅವು ಟೈಟ್ಲಿ ಬಾಂಡ್ ಆಗಿದಾವಲ್ರಿ, ಅಷ್ಟು ಅಮೌಂಟ್ ಆಫ್ ಎನರ್ಜಿನ ನಾವು ಇನ್ವೆಸ್ಟ್ ಮಾಡಿದೀವಪ್ಪ ಅಂತಂದ್ರೆ ಅವೇನಾಗ್ತಾವ್ರಿ, ಎಲ್ಲ ನ್ಯೂಕ್ಲಿಯಾನ್ಸು ಸೆಪ್ರೇಟ್ ಆಗ್ತಾವೆ. So that is nothing but the binding energy. Is this clear? The amount of energy required to separate all the nucleons from its nucleus, or the amount of energy required to break up the nucleus into its constituent particles, into its constituent nucleons, and that is nothing but binding energy. I think you get the idea. You just got an idea. That means nucleus contains protons and neutrons, and all these nucleons are tightly bound with each other. There will be the attractive force, and they are attracted with some amount of energy. This is clear. They are tightly bound with some amount of energy. To separate these nucleons, we have to invest, we have to apply some amount of external energy. And that required energy to separate the nucleons from its nucleus is nothing but binding energy. I think you get the idea. So now from where this binding energy comes into the action? So that is nothing but the mass defect. The mass defect. So here it is. Here it is. So according to the Einstein's mass energy relation, just go through it. According to the Einstein's mass energy relation, the mass defect of a nucleus is converted into the binding energy. The mass defect of a nucleus itself is converted into the binding energy. Right? Therefore, the binding energy of the nucleus is given by, we know that mass energy relation is given by E is equal to mc square. Right? E is equal to mc square, where E is energy and m is mass into c is nothing but velocity of light in vacuum. Is it clear? So E is equal to mc square. So now the binding energy is given by Eb, where Eb is the binding energy. It could be equal to delta m into c square. We will not take m here, we will take delta m. So because of the mass defect, there will be the binding energy. Because of mass defect, there will be the binding energy, right? So that's why we will take mass defect delta m into c square. So this is nothing but, this is the formula for binding energy. Binding energy is equal to what is the formula there? Binding energy is equal to delta m, mass defect, multiplied by c square. Is this clear? From Einstein's mass energy relation, E is equal to mc square. So here m is a mass and here delta m is a mass defect, because mass defect itself converted into energy, and that is nothing but the binding energy. Is clear? So mass defect is equivalent to binding energy. Therefore, binding energy is equal to delta m into E square. Delta m into c square. Sorry, delta m into c square. So Eb is nothing but binding energy, and that is equal to delta m into c square, where delta m is mass defect and c is velocity of light in free space. I think you get some idea about binding energy. So now the next very important point is binding energy per nucleon or specific binding energy. So binding energy is the amount of energy required to separate all the nucleons from its nucleus. The amount of energy required to break the nucleus into its constituent nucleons. That means here we are breaking all the nucleons. It is the amount of energy required to separate all the nucleons. But binding energy per nucleon is the amount of energy required to separate one nucleon. Right? So amount of energy required to separate one nucleon. It is also called as the specific binding energy. Specific binding energy. That means we are not spending the energy to separate all the nucleons, but we are spending the energy to separate only one nucleon. One proton or one neutron, to separate amount of energy to separate one neutron from its nucleus, one proton from its nucleus. That is the thing but the binding energy per nucleon, or specific binding energy per nucleon. The definition is given here through the look towards just have a look here. The average energy required to release a nucleon from the nucleus is called binding energy per nucleon. The average energy required to release a nucleon from the nucleus. The average energy required to release a nucleon from the nucleus is called binding energy. Release a nucleon. A nucleon means only one nucleon, either one proton or one neutron. Is this clear? So this is nothing but binding energy per nucleon or specific binding energy. Simply have a look here. The binding energy is the amount of energy required to separate all the nucleons. Right? Specific binding energy is the amount of energy required to separate only one nucleon. Is it clear? So that means this specific binding energy is nothing but binding energy per nucleon. Right? Binding energy per nucleon. So to separate all the nucleons, we will spend some amount of energy, and that is nothing but binding energy. So if it is multiplied by the number of nucleons present inside the nucleus, that will gives you the specific binding energy, and that is given here. So EBN is equal to EB divided by A, the binding energy per nucleon. So the explanation is given here. Just have a look here. For a nucleus, binding energy per nucleon or specific binding energy is defined as the ratio of binding energy to the binding energy of the nucleus into its mass number. That means binding energy divided by mass number will give you the specific binding energy or the binding energy per nucleon. So once again, I will revise all those things. Have a look here. Whatever we have discussed, first we have discussed the mass defect of a nucleus. So it is very important. That's why I'm just have a look here. The mass defect of a nucleus is the difference between sum of masses of nucleons forming the nucleus and the actual mass of a nucleus. So sum of masses of nucleons means Zmp plus A minus Z into Mn. So mass of a nucleus means minus capital M. That means actual mass of a nucleus means capital M. So this is nothing but the mass defect. That means the difference between sum of masses of nucleons and the actual mass of a nucleus is mass defect, and it is denoted by delta M, and mass defect is always given by the formula delta M is equal to Zmp plus A minus Z into Mn minus capital M. Next we have discussed about binding energy of a nucleus. Binding energy of a nucleus is the amount of energy required to separate all the nucleons from the nucleus, or the amount of energy required to break the nucleus into its constituent nucleons, and that is nothing but the binding energy of a nucleus. This will be given by the formula, that binding energy will be given by the formula Eb is equal to delta mc square. Eb is equal to delta mc square, where delta m is mass defect of a nucleus and c is velocity of light in free space. And we have discussed binding energy per nucleon. So binding energy is the amount of energy required to separate all the nucleons, and binding energy per nucleon or specific binding energy is the amount of energy required to separate a nucleon, required to separate one nucleon from the nucleus, and that is the thing but specific binding energy, and it is given by the formula. Here it is binding energy divided by mass number. Here mass number is nothing but total number of nucleons present inside the nucleus. Remember it, the mass number is nothing but total number of protons and total number of neutrons present inside the nucleus. That is nothing but the total number of nucleons present inside the nucleus. So the amount of energy required to separate all the nucleons divided by total number of nucleons present inside the nucleus, that is the binding energy divided by atomic mass number, will gives you the amount of energy required to separate one nucleon, the amount of energy required to separate a nucleon from the nucleus. That is nothing but specific binding energy. So I hope you guys understand this thing. Thank you very much. We will continue in the next class. Thank you.